Okay, we're going to look at a couple applications here in 3.8 and 3.9. First one is called Newton's method. And it's used to approximate zeros, real zeros for functions. Okay, so let's go ahead and start this. Okay, now over here I have a drawing of a function f of x. Okay, and we're trying to get to this zero right here. This is the goal. So we start with an estimate, and we call it x sub 0. Now, the corresponding y value is f of x sub 0. So here's the point. And I purposely put it away from the actual 0, which is over here somewhere. I'm not sure where. And to illustrate this, so what we do is we run a tangent from that point down to the x-axis. And that new point where it hits the intercept is x1. Then we write an equation for that line using this formula, the point slope form. So with my one point as x1, 0, okay, that would be the equivalent of this coordinate and this coordinate, because that's the variable. We don't know what that's going to be, the x1. But in any case, it will be determined by this point and the slope at this point. So this will be our equation then. x1 is the x1, 0 is one point, and x1, f of x0, that is a known point. Okay, so we don't know is x1. But this is x0, sorry. But we do know x0, f of x0. So throw that in here. The slope at the point is f prime of x0. Put it into this equation, solve it for x1. You're going to get this thing. This gives us the coordinate x1 right here where that line intersected. Now notice it, and this is what we hope to happen, and under certain conditions it will. It's closer to the original, to the estimated, well, to the actual point right here. Notice it moved over this way. Okay, so that's what we hope happens, and it will happen in certain cases. In certain cases it won't, depending on the slope of that graph. Now, of course, if f prime doesn't exist, then the method fails. Okay, it breaks down at that point. We have to try something else. But in any case, this is our general formula here. This is the one that we'll use. It's called an iteration formula. And it requires that we start with a given value, an estimate, and the function itself. Now, down here I have, on example 1, I have a table. And I'm not going to go through all this because it really, I mean, we could fill in these numbers, but this is really not very, we'll say, efficient. And I'm going to show you how to get this all done on the calculator in just a few steps, because we're not going to focus on this. We could build Excel tables and all kinds of things with this, but we're not going to do that for this one. We're not going to get into it that much. This is just a little intro to the topic. So, okay, so here's our function, and we, unless you're told what to do, then you would just estimate your 0. For here, I'm estimating a 1. I look at the graph and I'm saying, okay, it looks like about a 1. So I would start with a 1. So that would be what you'd put in here. And f of 1, of course, was pretty easy to get, is a 1, straight from here. F prime, well, you'll need the derivative. So f prime is equal to 5x to the 4th plus a 1. That would be a 6 then, if you put that in there. Now 1 over 6, and then xn sub plus 1, so it would be x. This value, this first cell here would be x sub 1. It would be the xn, which is 1, minus the 1 over 6. So that would be 5 over 6. Now down here is the difference between the two successive estimates. Or so for this first one, it would be 5 over 6 minus the 1, which is 1/6. Okay, so that's how far apart they are from each other, those two estimates. Now the next cell here, you would bring down your 5/6. That's your x sub n, the one we calculated over here in this cell. And then you would continue then computing across here, one step at a time, all the way across. Typically, the method would stop when the difference between two successive estimates, in other words, the difference between these two and the difference between these two would be in this cell here, the absolute value of the difference. And then when I get my next entry in here, which would be x sub 2, then I would find that difference and put it over here. When that difference becomes small enough, acceptably small enough, then you would stop. Okay, so now here's how it's going to work in the calculator. Okay, first of all, you put your function in here. F of x will come in here. So we'll have x to the 5th plus x minus 1. Okay, now we also want the derivative. So that's easy enough to do. We already did it. It's 5x to the 4th plus 1. So we'll put that in there. So once those are in place now, you leave the screen and come in here. Now, I want you to put your estimate here. My estimate is a 1, and just enter it. Okay. Now, I want you to put in the formula. This part of the formula here, the xn minus. So we're going to put that in. Now, the xn is my answer. So in other words, my answer in the display. So I'm going to put that in. I'm going to subtract f. And here's how I get that under variables, y variables, function, y sub 1, and put the answer in there. And divide it by, go back to variables, y variables, function, and then function number 2, also evaluated at the answer. Okay, so that's our formula. That's Newton's formula. This will give us the x sub n, the next value of the x sub n. So let's look at that. Now there's the 0.833, and that is the 5/6. That's the 5/6 that we calculated over here. Okay, so now the good thing about this is all you have to do, since this is the new answer, is to pull up the previous line on the calculator and enter once more. So in other words, I'm gonna do second entry. Now this will take the answer that I just found and put it in again, but that's the whole iteration process itself. So I press it one more time and I get my next estimate. So if we were working on a table, that 0.764381 be the number over here, 76438. So that'd be over here. And of course, keep as many digits as possible to keep this keep us from losing our accuracy along the way here. So that's the next estimate. And of course, you can find the difference between those two and put that over here. Now that's not built into the calculator. You'd have to do that yourself with an extra computation. But back to the calculator now. Let's do it one more time now. Second entry, enter. There's our next estimate. 0.755024. 0.755024. Okay, and then if we keep going, let's repeat that again. 0.754877. Okay, and let's do it again. Let's see what happens. Now notice at this point we are really close. I mean, because the difference between these two is negligible up to the 1, 2, 3, 4, 5, 6 decimal place. It's the same number. So the difference between these would be less than 1, 2, 3, 4, 5, well, tens, hundreds, thousands, 10,000s, 100,000s, almost to the millionth decimal place. These two numbers agree. One estimate versus the previous estimate. Current estimate, previous estimate. So at that point, you might say, well, that's probably close enough, or you can keep going. Let's do it one more time. Now notice there's no difference. The calculator is not giving us, it may be holding more accuracy than this, but it's not showing it. So we'd have to be satisfied with this, that out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 decimal places. We got that after like about 6 iterations. I wasn't keeping track here. So we would stop at that point. We wouldn't keep going. We're not going to get any closer. So that's the method. When it works well. It's one of the approximation methods for finding zeros, not the only one. There are many others, and you would just study those in a numerical analysis class, numerical methods class, and you discover others that are more efficient, more rigorous than Newton's method. But this is a good use for the derivative. It's kind of an ingenious way to discover zeros. Of course, without the calculator, lots of arithmetic here, lots of number crunching, and you would have to do all that without a calculator. But we're focused on the actual application itself, the idea of the application. Okay, so let's call that quits then. That's good enough.